this will be about text classification with Lucene, Solr, and LibSVM. I'm Majirus Fansi. I work for Valtech SA, an IT company based in Paris. We advise our clients in turning their projects and organization agile, and also we help them develop their project. We participate in their product development. Before showing the outline of this talk, I would like to start with this motivating our motivations, that is guiding user search. You all know that search engines are basically keyword oriented. So the question that comes to mind is, what about the meaning? During these 2 days, we hear about semantic search, about meaning in search engine. And in Solr, you can use synonym search. But here, you need to list all of your synonyms in a file. But there are situations where you don't have the synonyms in the first place. So you cannot really exploit this functionality. You can also use more like this component. But as we write here, more like this is about more like this. So you have to have the gist in the first place. If the user query cannot target any document in your collection because the keyword is not available in the collection, you have nothing, so you cannot apply more like this. And that is why we are going for category search. And here we want to apply category search for better user experience. So here we deal with the cases where user keywords are not in the collection. User search is for example, for e-marketing, and you return documents on web marketing. You know that they have the same meaning, but it's not the same keyword. It's not the same token in Lucene directory. So in this talk, we will explain what is text categorization. We will also introduce machine learning, because we are using machine learning for categorization. The algorithm we will use is based on SVM. We will explain SVM and show how it works internally, because we need to know that in order to take profit of some functionalities, namely extending user keyword. And we will also show how Solr can help here, because Solr is a major component in designing the categorization task. So what is text categorizations? The aims of text categorization is classify document into a fixed number of predefined category. So a document can be in multiple, exactly one or no category or at all. And this has many applications. We hear just before lunch, one application of this is classifying emails to spam or not spam. And we show here also another use case, guiding user search. So we will extend the user keyword in order to target documents that do not contain the keyword the user sent to the search engines. But this comes with many challenges. First, you can't build text classifier by hand. It is very difficult and time-consuming. Just suppose that this morning we saw that in Career Builder they have 2.5 million jobs posting every month, and if they say, okay, you come and label each document. Say, okay, this is a Java job, this is a .NET job, and you have 2.5 million documents like that. You can just accept the job. And so it is advantageous to learn classifier from examples. And what we would like to see here is learning. And this leads us to the machine learning. We will train the machine to learn itself. So let's start by the definition by Tom Mitchell of machine learning. He said a computer program is said to learn from experience E with respect to some task T and some performance measure P, if it is performance on T as measured by the performance measure P, improve with experience E. So that is the well-accepted definition. And when you are designing a machine learning, you are writing a machine learning application, you have to define what is your experience. For our case here, it's watching the label of a document. So we'll show a document to the algorithm, say, okay, look, this is a Java job, right? Because Java is a category we want to have at the end. This is a Java job, he just learned from that. The experience is watch the label of a document. The task will be to classify a document. So further we will send a document and say, from which class is this document? And the performance measure is the probability that a document is correctly classified. That's the performance measure. So when we send document, we expect the performance, the probability to grow, that document is correctly classified. So when you are dealing with machine learning, you have two types of algorithms. You have unsupervised learning and supervised learning. In unsupervised learning, you let the algorithm learn by itself. You get some t-shirt here from LucineWorks. You can imagine that LucineWorks say, okay, we need an algorithm. We just take information from the attendees in this conference. We give that information to a machine and say, okay, we need three clusters here because they just need the size L, XL, and XXL. So the machine says, okay, with this information, we can provide these three clusters. And then from that, the experts there say, okay, we will take these people to L, take this one to XL. And then from those information, because they know the number of persons in each cluster, they can order t-shirts with those information. That's an example of unsupervised learning. It is heavily used in market segmentation, in social network analysis. But we here are interested in supervised learning. Here we teach the computer program how to do something. So we give the algorithm the correct answer via a training set. Say, okay, look at this. It's like training, helping a kid with the alphabet. You say, look, this is A, this is B. So next time he knows it is A because he was told that it's A. And that's what we are going to do here. So in the supervised learning, you have two types of problems, regressions and classification. Regression is just about predicting a continuous value output, like the price. You want to know the price of the houses in Corbeil-Essonnes in France. So maybe you just provide the algorithm with some examples of house, the characteristic, and the price. And then next you say, okay, I have a house. This is the characteristic. And then you say, okay, maybe it is 300,000 euros. And you also have, the other type of problem is classification, where you predict a discrete value output. And here is where we are going. We are predicting 1 for Java, 2 for .NET, things like that. So how does this work? You start with a training set of M training examples. X, I, Y, I is the ith training example. X is the input variables or features, and Y is the output or target variable. You provide this to your training algorithm, and it is the role of the training algorithm to produce the model you will later use to classify new document. So he produced the hypothesis. Then later, when you provide an input vector, a feature vectors to the algorithm, then you return a predicted value. And this works for regression and for classification. That is how supervising learning works conceptually. Now, internally, the algorithm defines something called the decision boundary. That is, it carves up the feature space into volumes. And feature vector in the same domain is assigned the same class. So here I may have the green as a negative and the red as the positive. Decision regions separate the surfaces. So you will bring decision boundary like this, for example. And this decision boundary is said to be linear if it's a straight line in the dimensional space. So if you are in 2 dimensions, like here, it is a line. In 3D, it's a plane, and generally, it is an hyperplane. Now, we see what is about machine learning globally, but we want to apply this to text to provide a text classifier. So we need to know the properties of the text we are going to study. First, we know that text has very high dimensional input space. So you can have more than 10,000 features. Just imagine a Lucene index. The number of terms in a Lucene index can be the number of dimensions you have, because in text classification, each token is a dimension. So you have 1 million token, and you are building a text classifier on this collection, you may have 1 million dimensions. So it is a high-dimensional input space. You have very few irrelevant features. That is first a bad thing, because you cannot use feature selection. You are stuck with all these features, and you have a high-dimensional input space. Document vector are space. You remember what search engine designer take like invert index rather than a matrix of term document because of this, these properties of document vector. But research showed that most text categorization problems are linearly separable. That is, you can find a linear decision boundary in most text categorization problem. That is a properties of text. So, because you have very few irrelevant features and you are in a high dimensional input space, there is no need to map the input features to a higher dimensional space. And in some algorithm, you don't have this property, so you use something like kernel to map to a higher dimensional in order for your algorithm to generalize well. But here, you don't need this. Now, how do we choose a method, the method? That is the question we ask ourselves when we start to build our text classifier. So we read this article by researcher Thorsten Joachims. He published a comparison of algorithms, and he showed that SVM consistently achieved good performance on categorization tasks over the other algorithms. So he showed also that SVM eliminates the need for feature selection. Good news, because we have very few irrelevant features. If he can deal with all these features, we are lucky, and that's the case. And he also showed that SVM is more robust than the others. So for some size, some algorithms here just break, but SVM was still up. So you can understand that from this, we are going for SVM as the method for our learning algorithm. But I would like to cite this from researcher Banco and Brill. They say the research community should direct effort toward increasing the size of annotated training collections, while de-emphasizing the focus on comparing different learning technique training only on small training corpora. This was, I think, in 1998 or 1995, because there was too many comparisons about learning algorithms. And what the researchers are showing here, are highlighting here, is that the size of your training corpora is important. And also, you have annotated the training corpora. It is important that you have a good annotation. If you take a Java job and say to your learning algorithm, this is a .NET job, it's like saying to a kid that A is C. You see what I mean? So you can't expect much from that. But what is good is that the comparison researcher Thorsten Joachim made was in a very large training corpora. So we have most extensive following such a result, because he's not in this situation where people use just small training corpora. Now that we are using SVM, what is SVM actually? Or super vector machine. The good reference for SVM is the work by Cortez and Vavnik in 1995. It is super vector networks, but today it's mostly called super vector machine. In this paper, they show that SVM implements the following idea. It maps the input vector into some high-dimensional feature space Z, and through some nonlinear mapping choosing a priori. You may say, okay, in text classification, we don't need to map to a higher dimensional space because it is already in a higher dimensional space. But SVM is a general algorithm. So you can use a linear kernel so that your input vector is already in the feature space. So you don't need to map this. It's a general idea, and here we are presenting the general idea. So in this feature space, a linear decision surface is constructed. So SVM is about constructing linear decision surface. And special properties of the decision surface ensure high generalization ability of the learning machine. So that is, your algorithm will, if your algorithm is effective in your training set, you can expect from SVM that it will be effective also in unknown examples. So how does this work? You start with the input vectors. This is through nonlinear transformation mapped to another input vector in the feature space. But in the case of text classification, you are in the same space here. Then the model, using some special vectors, it's going to construct by itself, called support vectors. Thus the name support vector machine. The support vector now will internally use some kind of dot product on your input vectors to return the class of your input document. And you can use multi-class classification, but the definition, the original definition is about binary classification. But you already want to know before whether it is positive or negative. It's binary classification. So the decision boundary in SVM are of two types. You have the optimal hyperplane and the soft margin hyperplane. The optimal hyperplane is the original one, the first result. It's just say that it's just separate training data without any errors. So you have the positive and the negative. You have no error, zero error. That is the optimal hyperplane. And in the soft margin hyperplane, some error are tolerated. The soft margin accepts some error in order to keep a large margin, because SVM is sometimes called also large margin classifier. So we will start with the optimal hyperplane, because even if you are using a library, general library is a soft margin, but the goal of the soft margin is to finally get results similar to optimal hyperplane. So how does this work in the feature space? You have here two classes. You have the red and the blue. And here, the hyperplane, you can draw the hyperplane like this. You have separated. You have the blue on one side, the red on the others. You can also have this. You can draw many hyperplanes like this. But what the SVM will do, he will come here and draw something like this one. That he will call the optimal hyperplane. And the property of this is that, one property is that he has very optimal margin. That's the large margin he can get from this space, given the examples. And in this feature space, you have these special vectors on the decision boundary for each class. And these special vectors will be called support vectors. And whenever the SVM has built its support vectors, you don't need the other vectors anyway. You just use the support vector to classify your document, because the optimal hyperplane is just a property of the support vectors. I'm showing a bit of math, because it is important when you are using a software like this, how you can really benefit from all of its properties. And we will see from this math that some properties are really interesting. So we start with a training set. And then the optimal sweeping set is linearly separable if there exists a vectors W and a scalar B, so that the two equations 1 and 2 holds. That is the properties of the constraints of the SVM. You are not required to implement this. Software package already implement this. And 1 and 2 can be summarized as 3. And in this setting, vector xi for which you have yi(w.xi plus b = 1 is termed support vectors. So the SVM will search for this vector, for vector xi. And these vectors are used to construct the hyperplanes. And it is shown from Valtech papers that if the training vectors are separated without errors by an optimal hyperplane, the following property holds. And it is a very interesting property because it says that the expectancy of the probability of committing an error on an example is bounded by the expectancy of the number of super vectors and the number of training vectors. You see, if the SVM can devise a small number of super vectors relatively to the number of training set, you have very nice properties here because it means your algorithm will generalize very well. You have the chance to committing an error will be very low. And that's a nice property of super vectors, and that's why super vector algorithm will try to find very small number of super vectors relatively to the training vectors they have. So the optimal hyperplane is the unique one which separates the training data with a maximal margin. So the goal of the algorithm will be to find this. It's the unique one. Some other equations, because it's important in our setting. So let's consider the optimal hyperplane is W0.z plus B0 equals 0. It is shown that the way W0 can be written as some linear combination of super vectors. So you see there that the decision boundary depends only on super vectors. It is, if you inspect this alpha I, because SVM package provide you at the end of training with the vector W, and if you inspect the alpha I, you can see the most predictive terms. Because they are in the order, you can see that, for example, the alpha I for the term Java is weighted like 1.5 in the Java class. Alpha I for G2E is like 1.2. Alpha I for .NET is like -1. It means if you send a document to that that classifier for Java, for the class Java, with .NET, you are increasing your chance to have a negative output. And if you are sending Java G2E, the most predictive term, you are increasing your chance to have a positive output. So the linear decision function IZ is of the form, is a sign of the sum over the super vector of the alpha IZI dot Z plus B0. And you see here you have, it is like W0 dot your input vector Z. So and ZI dot Z is a dot product. So you see, it's about of the component you have in your training, in your test example. If it does not share some component with the super vectors, but those components will be weighted 0, and they won't be used in this decision function. That is why I showed this equation, because it's important to know that. Now, that is the optimal hyperplane. But in the real life, you can just separate without error. You have some error. Some error are tolerated. That is why Cortez and Vamnik propose soft margin hyperplane. Here, we want to separate the training set with a minimal number of errors. So phi C here is just the number of error. By default, sigma is implemented as 1. And you see the constant here change. In the left-hand side, you have 1 minus epsilon I to tolerate the error in some examples. The functional files here describe the number of training error. And it is clear that removing the subset of training error from training set, you will have, as the remaining, you can separate the remaining part without errors. You will have optimal hyperplane, because you already removed everything with error. And this is why we first look at the optimal hyperplane, because the goal of the soft margin is to isolate some error and construct the optimal hyperplane on the remaining. So in machine learning, whether you are using logistic regressions or neural networks, you have the optimization objective. And the optimization objective for SVM is the following. It's the minimizing W square plus some constant C times the number of errors. And under the constraints we have here at equation 8. And to simplify things, for sufficient large C, the vector W0 and constant B0 that minimize 7 under constraint 8 determine the hyperplane. That has the following properties. It minimizes the sum of deviations because you are minimizing this expression and you have the sum of deviation there. So the objective is to minimize the sum of deviation. We don't have too much error. We don't need too much error. Also, we want to maximize the margin for correctly classified vectors. And I'm not showing the math here, but minimizing the dot product W square is shown that if you do this, you maximize the margin between correctly classified examples. That is why this part of minimizing W square is about maximizing the margin, and the other part is about minimizing the number of error. And you are good with that. And sometimes you also hear about model selections. Model selections here refer just to choosing the constant. You have two constants here, C and B. So model selection, sometimes you keep aside a number of examples for cross-validation, and you tune just C and B. That's all you can do in SVM. You provide a value and C, you can see C is 1, B is 1. You take the result, C is 1, is 2, B is 1. And then you have some kind of matrix, and you choose the best value of C and B for your examples. But we usually use C as 1 and B as 1, and OK, it's OK. So the soft margin graphically is looked like this. We take our previous examples. Then we introduce two errors. We have one red here and one blue here. If you are to separate this, you can say, OK, I will draw a vertical line so that the blue will be on the right and the red on the left. But the SVM may keep these separators. Then, then he ensures this soft margin. It is soft margin now because there are some elements in the boundary here. You have the red here, and the error for the red here is less than 1. So in this case, the red one will be correctly classified, given the property 1 minus epsilon. But the blue one will be misclassified, and this is accepted by the model in order to keep this large margin. So here you will have one error. The blue one will be labeled 1, but the model we see minus 1 because of the decision boundary here. So that is SVM and how it works. Now, we want to apply it to construct our text classifier, right? So we need a library. That is just math, which is about scientific papers. But we developers, we need library. You don't find a library, you have to write it by yourself. But we have a chance that efficient optimization packages are available. We have SVM Lite and libSVM. We also need to convert text to feature vectors because this is about vectors, about dot product. It is a numeric calculation. It's not about text. We have to choose between multi-class classification and one versus the rest. We choose one versus the rest, and I will show by the end of this a scientific paper that supports that choice of one versus the rest. And another good reason is that when you are building a multi-class, so you build a model and you say, this is class 1, this is class 2, this is class 3. But what if you don't know all of your classes in the first place? So tomorrow you need another class. So we just decided that, OK, if we need more class, we just build that class without inferring on others. Using another aspect of what we are going to do is using the categories for semantic search, because that was the ultimate goal, extending user query for better user experience. So we use dedicated Solr index with the most predictive terms. And to get the most predictive terms, you see the weight vectors, we have to take that vectors with the dictionary and use some kind of cross relation to output the most predictive term. That is why I show those mathematical equations. So regarding SVM library, SVM Lite, we go for libSVM developed by this researcher from Taiwan University because it is under heavy development and testing. And they have a library, it's right in, you have a package in Java, in C, in Python, in R language, MATLAB, and also Octave. So depending on your language, you will find it. And you also have libLinear. This talk is about classification with libSVM. SVM, we put libSVM in the front side because it's about the SVM model. It's about the SVM algorithm. But what we will really use is the libLinear package developed by the same people who develop libSVM. And why? Because libLinear is just a brother of libSVM, and it is optimized for large-scale linear classification. This one is recommended by the authors of libSVM for things like text classification. They say, okay, you are doing text classification, things like that. We have libLinear, that is a special package optimized just for that. And that is why we will effectively use libLinear. So libLinear, it's a library for large linear classifications. It supports binary and multi-class, but we are using binary because we use one versus the rest. One versus the rest, it just means that I have an input vectors. I query the Java class, the Java classifier. Is this from you? You say yes or no. And query.net, is this from you, yes or no? And a job may be in two classes. And also with this, you can direct the recruiter. You see, he just posts a job, then you send to the classifier, and you say to the recruiter, oh, look, your job is targeting Java developer and .NET developer. Is really this what you need? And you can even go further and say, look, for Java developer, you use this term, using your most predictive term for that class. You can say it is saying that it's a Java developer because you write this in the job in the job qualification requirement, and it is saying .NET because you write this one, and so it is very important. So the format of training and testing data file is the following. You have the label, it's the left one. Then you have index value. You have this couple, index value, index value. Each line contains an instance, one instance per line. So each line is a document that with its label. That is the training example. It's the same for the testing example, of course. Each line with its document, and label is just an integer indicating the class level. Because we are using binary classification, label is just 1 or -1. The pair index value gives a feature value. Index is an integer starting from 1. This is a constraint of the package. You start with 1. And value is a real number. So you choose what you need as value. This is, just wait at this. It doesn't matter whether you are, it's not the role of the algorithm to ask what you are doing with where you are taking those values. No. Indices must be in ascending order. That is another constraint for optimization objective. So an example input file is the following. You have 101 as index with the value 1, and the following. You have another line, that's the negative example you provide to the training algorithm. And you don't have to represent the zeros, because if you don't represent something that does not matter, you save space with that. So to build this, we need a dictionary of terms in lexicographical order. So we will have a dictionary like this. We have at position 1, we know it is .NET. At position 2, you see it is AA. In position 6000, it is Java. In position 7565, it's Solr. This is extract from our training example. And now from a document, if the document contains Java, then in my input file, the index will be 6000. And the value, we will see what we choose as value. So to do this, to construct a dictionary, we divide the overall training data into a number of portions. And in the SVM research paper, it is shown that if you can't find a linear decision boundary in a portion of your document, it means that maybe you won't find it if you take the entire collection. And we use the domain knowledge here, because if I take someone here, I show a job on search engine, you will say, yes, this is a job on search engine, because you are an expert. And if I say, okay, you use Solr, write a Solr query to retrieve each job posting on Java, maybe with Lucene and Solr, you will write it without any problem. That is why we use Solr for this. First, we index without any category. We have our large collections. Then, with the knowledge of the domain, we can devise portions. I can devise first portion for the application development, where we will have Python, CGS, .NET, Java, and others. This is a domain of application development. I may have another domain for marketing, another domain for accountants. So I use different domains. This avoids very large dictionary, because I have one dictionary per domain. I avoid very large dictionary. So because a Java dev position, as I show here, has, and a marketing position share few common strengths. So we use expert Boolean query to load a dedicated Solr core per domain. This is just an illustration of expert query. I know if I look at a job, there are Python in the title of that job, and there is also Python in the description. There are good chances that they are looking for a Python developer, right? That is why we collect things like this to devise different collection with expert Boolean query. And this is another course, right? Not the code the user search in. So we build the dictionary with Solr. What do we need in the dictionary? We need terms properly analyzed. We lowercase so that it's not case sensitive. Stop filter. There are some common terms we don't need in our dictionary. It has no means for our domain. ASCII folding. I'm working in France and we have accent everywhere. Snowball porter filter. You remove superficial text from your index. So we use Solr's term vector component to retrieve this document, because with this attribute tf.tv.gf, you return the document frequency per term. You can also get with tf the term frequency. You can specify the field list where you want it, and we have a catch-all field where we aggregate information we want to send to the classifier. So you just set term vector like this, and nothing new here. Solr Wiki is very good documentation for this, how to configure Solr to query term vectors. And then you have to construct training and test set per model. So domain expert query is used to extract document for each category. TVC returns the term info of the terms in each document. Each term is replaced by its index from the dictionary. And this is the attribute then. And you need the value. Here, we decide to use the term frequency info as the value. Some use the presence or absence. Others, TF-IDF. We refrain from using TF-IDF because we think it's not a property. The fact that a document is a Java, is from Java collection, is not a properties of the entire collection. So we don't need TF-IDF. TF is enough. Then we shuffle document set so that high score doc do not go to the same bucket, and we split as you. This is our approach. We have 60% for the training set, 20% for the validation set. It is positive in our model, and when we use it for other models, it's negative. 20% is used for other class training set, because in the other class, you have to show the negative example. So this 20% will go there. And we try to have a balanced training set, so that something like 50% positive and 50% negative. It is a good practice from the libSVM developer. The model file is safe after training. You have something like the one model per category, and the model contains this. You have the solver type. You choose it first, but you will see it from the wiki of libSVM why we use this. It's not matter. The number of class is printed. You have the label. You have the number of features. You need for the development core. We have nearly 9,000 features, and you have the bias. We choose always one, and then we have the vector W that. It shows the alpha I for the different terms. So the first term in the dictionary in this Java, this was for Java, and was .NET. .NET weighted minus 0.1. That means it is not a good fit for Java collection. And we remind you about these equations because W will be applied to Xi. And the result should be greater than 1 if you expect Yi to be 1. So you see, if it's negative here, you are going far from 1. So the model file contains vector W. The W, we use W to compute the most predictive terms of the model. This gives an indicator as to whether the model is good or not, because it's not possible that .NET is a most predictive term for Java position. You are the domain expert, so you read this, you understand immediately. Useful to extend basic keyword search to provide semantic search. And that is all. For semantic search, we create a collection, a new core in Solr. Each document represents a category. One field for category ID, and one multivariate field holds the top predictive terms. So when the user query comes, we can run the query in this core, and it shows us the most, it will target some predictive terms and show us the category of those predictive terms. And because the user query sometimes is 2 words, 2 terms, it's very short. And indexing time, each document is sent to the classification service. We have a service outside Solr, of course. The service returns the categories of the document. Those categories are saved in a multivariate field along with other domain pertinent document fields. So we just add that category field. And the user query will be extended with this. So when it's executed in the category core, we take the category, we extend with ORing the query, and then with boosting mechanism. So that's what we say here. User query is run on the category core. And the returning categories are used to extend the initial query. We affect a boost less than 1 to the category so that the user query still has more power than the category. We are not replacing the user. We are helping user finding what they are looking for. And we say here, what about libshorttext? This is a library from the authors of libSVM. It is relatively new. And the goal is to classify very short text, as its name implies. And the next step for us is to use libshorttext to classify the user query. We will use Solr for this. We will take many, user will help us. We will take many query and then classify them as we are domain expert. We will classify and then run libshorttext. And maybe we will just use another classification service for user query and not user just, we will test that. I can't say more than that. So the references are this one, Cortex and Vapni Super Vector Network, libSVM library, liblinear, Thorsten is working on text categorization, and this work by Rick Fink and Clauto about the difference of one versus the all classification. That is what I can say for today sessions. And I can close this without saying a big thank you to the Lucene Solr Revolution organizers. Special thanks to Megan Burks and her teams. I know particularly I sent many requests, administrative one, technical one, and they were always available. I know you have invested a great deal of energy for this conference. Thank you for that. Thank you to the management of Valtech to have allowing us time to explore these problems. I can say more to my kids and my wife because to prepare this, you have to be outside of the house late. You came back, they are already sleeping, and the next morning they just show their love. So thank you so much. And of course, thank you so much to all of you for your presence and your attentions. If you were not there, I think I will be in France now. Thank you so much. If you have any question.
So when you're working with a support vector machine in the soft margin scenario, I was wondering if there's any way, since you know that you're going to misclassify some of them, is there any way that you can pull out something like a probability of correct classification? Do you know what I mean?
No.
If we're in that soft margin, then we know that a portion of the time we're going to misclassify these. Yeah. But if we're towards the edge of it, then we can say we declare this to be set A, but with only a probability of 90% certainty. Is that available from the math anywhere, or does that seem plausible?
No, I can't say it's impossible. Something that I'm not doing today. But I answer another way. If you run your classifier or your training examples, you have a test set, but you can test your classifier with the training example. If you have something like 90% accuracy or 95% accuracy, you can look at your classifier on your training example, which documents are misclassified. You see, because you already have that one. They are misclassified, but why? You can inspect first that document, and maybe they are misclassified because they have some term mixed, and maybe it can be a mislabeled example. You see what I mean? So maybe you run the first query in Lucene, and it browse something, but with very less relevancy, and you just take it as a candidate for your class. So you can just do your training set and expect which one are misclassified. Okay, thank you so much, guys, for attending this.